K Pure Math Unit 2, Paper 2, 2024. Let us begin. So question 1, given that 3y squared minus 4xy plus sin xy equal to 5, determine dy by dx. So it's obviously an implicit differentiation problem, so we're going to differentiate implicitly. So term by term, let's differentiate. So differentiate 3y squared, 6y, dy by dx, applying the chain rule. Negative 4xy, we're going to treat a negative 4x and the y as two separate functions using the product rule. So differentiate negative 4x, that's negative 4. We keep the y, plus, we're going to alternate now, differentiate this time now the y. We'll get dy by dx. We'll leave a negative 4x alone. Plus, again, sin xy. We're going to apply again the product rule. So differentiate the xy. So differentiate x, we get 1. So it's 1 times, use bracket here, so it's 1 times y, which is y. Plus, differentiate y, we get dy by dx times x. We'll leave x alone. And of course, sin differentiated, we get cos, so that's cos xy. So angle doesn't change. And differentiate the right hand side, differentiate any constant, we get 0. So let's expand the bracket now. So we have 6y dy by dx minus 4y. Dy by dx times minus 4x, that's minus 4x dy by dx. Next, we're going to distribute the cos xy to each term in the bracket. So cos xy times y, that's y cos xy. And cos xy times x dy by dx, that's x dy by dx times cos xy. So now we are solving for dy by dx. So we want to factor all the terms, factor dy by dx from all the terms. We have a dy by dx, so dy by dx, factor dy by dx from this term. We're left with 6y. Factor dy by dx from this term. We're left with minus 4x. And factor dy by dx from this term. We're left with x cos xy. The other terms, we can just group them on the right hand side. So group negative 4y on the right hand side is positive 4y. And group y cos xy on the other side is minus y cos xy. So to solve for dy by dx, we simply divide both terms by the bracket. So divide both sides, sorry. So 6y minus 4x plus x cos xy. Divide the right hand side by the same thing. So 6y minus 4x plus x cos xy. So that cancels that. So we have our expression for dy by dx. So dy by dx is whatever we have on our right hand side, 4y minus y cos xy all over 6y minus 4x minus x cos xy. Part B, differentiate cos inverse 3x minus 2. Express your answer in its simplest form. So we know that the derivative of cos inverse u with respect to x is negative u prime over root 1 minus u squared. So we know that u here, so using this, u would represent whatever is in the bracket. So if we differentiating cos inverse 3x minus 2, with respect to x. So 3x minus 2 will represent u. So u prime is just u differentiated. So differentiate u, which is u is 3x minus 2, differentiate that to get minus, so minus u prime, and u prime is positive 3. So it's minus 3 all over the square root of 1 minus u square, and of course u is 3x minus 2. So 1 minus 3x minus 2 all square. And we're asked to simplify this, so let's simplify by expanding the bracket. So this becomes minus 3 over the square root of 1 minus, and now we're going to square the bracket. So square 3x, that's 9x squared, minus 2 times 3x times minus 2, so that's minus 12x plus 4, and of course we can expand this bracket. So we're now with minus 3 over root 1 minus 9x squared, so distribute the negative to each term, plus 12x minus 4. So we distribute negative 1 to each term in the bracket. So we end up with minus 3 upon the square root of minus 9x squared, put the quadratic first, the x squared first, minus 12x. And if we group the constants, it's 1 minus 4, that's negative 3. Well, it's positive 12x. Positive 12, negative 9, and 1 take away for negative 3. Alright, so that's the best we can do with it. Next, we're asked to use partial fractions to show that 2x plus 1 over 3x squared minus x minus 2 is equal to all of that on the right hand side. So what we can do is let 2x plus 1 over, and of course, we want to factorize the, and the factors are given to us already. Factorize it, the numerator, the quadratic denominator, sorry. We end up with x minus 1 bracket 3x plus 2. And of course, you can do a quick expansion just to ensure that we factorize the quadratic there correctly. So we let it be equal to a over the factors x minus 1 and b over 3x plus 2. So our job is to prove that a is 3/5 and b is 1/5. Alright? So what we can do next is times. We can times both sides by x minus 1, the denominator on the right and the left hand side there, x minus 1 times 3x plus 2. So if we times the left hand side by x minus 1, 3x plus 2, the entire denominator cancel, leave us with 2x plus 1. If we times a by the said thing, the x minus 1 will cancel, so we'll left with a times 3x plus 2. And if we times b by same thing, the 3x plus 2 will cancel, so we're left with b times x minus 1. So to find a and b, we can let x be equal to several things. So what we can do is we can let x be equal to, what makes this bracket 0? 1, let x be equal to 1. So replace x with 1, 2 times 1 plus 1, that's positive 3. 3 times 1 plus 2, that's 5, so that's 5a. Divide both sides by 5. So a is equal to 3/5. Next, we can let x be equal to, let x be 0. It doesn't matter what x is. really doesn't matter. It won't affect the answer. Let x be 0, so 2 times 0 plus 1, that's 1. If x is 0, this bracket here will be 3 times 0, which is 0, so it's just 2a. And if x is 1, this will be negative 1 times b, so that's negative 1b. So we are solving for b, so we can just switch the b over here, become positive b, bring over the 1, equal to 2a minus 1. Now we know the value of a is 3/5, so it's 2 times 3/5 minus 1, and of course we can rewrite the 1 as 5 over 5, since we have a denominator of 5 here, so we can rewrite 1 as 5 over 5. So what we have here for b is 6 over 5 minus 5 over 5, which is actually 1 over 5. Since denominators are the same, we can just subtract the numerators. So that's 1/5. So a is 3/5 and b is 1/5. So it makes sense. So therefore, replace a with 3/5. So replace a with 3/5 and replace the b with 1/5. So we have just completed the proof. Let's continue. Hence or otherwise determine the integral of 2x plus 1 over 3x squared minus x minus 2. So we have just shown that all of this thing here is equal to, so we have, remember we rewrite 2x plus 1 over this. So we have just shown that this is equal to 3/5 x minus 1 plus 1/5 3x plus 2. So we have just shown that in part 1. So we can integrate using log, natural log. So this is 3/5 log x minus 1. And this is 1/5 log 3x plus 2 plus our constant c. Now, always check if you integrate correctly. So by differentiating. So differentiate log x minus 1. That's 1 over x minus 1. Differentiate log 3x plus 2. That's 3 over 3x plus 2. So we'll have a 3 in the numerator which we need to get rid of. So we divide this by 3. So it's actually 3/5 log x minus 1 plus 1 over 15 log 3x plus 2 plus c. Let's move on. Given that x equal to 2t minus sine t and y equal to 1 minus cos t, determine d2y by dx squared. So before we can find d2y by dx squared, we first have to find dy by dx, and dy by dx is actually dy by dt divided by dx by dt. So dy by dt, differentiate y, differentiate 1, we get 0. Differentiate negative cos t, we get positive sine t. Well, differentiate cos is negative, so the double negative, you end up with positive cos, positive sine, and differentiate x with respect to t, differentiate 2t, you get 2, differentiate negative sine t, that's negative cos t. So this is dy by dx. Now, the second derivative, d2y by dx squared, is equal to the derivative of dy by dx with respect to t divided by dx by dt. So that's a formula for d2y by dx squared. So we're going to differentiate dy by dx with respect to t. And notice it's a quotient, so we're going to be using the quotient rule. Alright, so differentiate dy by dx. We end up with differentiate sine t. We end up with cos t. Differentiate the numerator times the denominator minus, and then we're going to alternate. So this time we're going to differentiate the denominator. Differentiate 2, you get 0. Differentiate negative cos t, what you end up with is sine t. Times the numerator, which is also sine t, all over the denominator square, and the denominator is 2 minus cos t, all square. So that's the quotient rule there we're applying. Alright, so all of this is this. And then we're going to divide now by dx by dt. And remember that dx by dt is 2 minus cos t. 2 minus cos t. Put that over 1. Alright. Let's see if we can simplify a little bit. So we end up with, if we expand, this is, well, I'll leave it alone. I don't think we need to expand. This is cos t times 2 minus cos square t minus sine square t, because sine times sine is sine square, right? Minus sine square t all over 2 minus cos t all square. And we can, this is times, and we can reciprocate 1 over 2 minus cos t. So in the denominator is actually 2 minus cos t cube. So it's really 2 minus cos t cube in the denominator. And in the numerator is actually 2 cos t. Now, minus cos square minus sine square. It's actually, we can factor out minus 1, and we end up with actually cos square t plus sine square t. And remember, cos square t plus sine square t is actually 1. So this was negative 1 times 1 is just 1. So the simplest is 2 cos t minus 1. 2 cos t minus 1 over 2 minus cos t all cubed. It's probably the best we can do with it. Let's move on. Question 2, part A. Determine the integral of e to the 2x sine 3x dx. So this is integration. This is what we call by parts. So put the by parts formula. So the by parts, use the by parts formula. So the by parts formula, we have two representation. But I'll be using the one that says the integral of v times u is equal to v times integral of u minus, I'll sign there, integral v prime, that's v differentiated. And of course, this integral, we repeat it in the second part, alright? That's the formula I'm using. So I'm going to let my 3x sine 3x be u, and e to the 2x be v. Alright, so we're integrating e to the 2x sine 3x. Alright, so no, I'm just following this formula. So from a v, my e to the 2x, I restate that. And I integrate u, integrate sine 3x, integrate sine, that's negative cos. So it's actually negative cos, so I'll put negative outside here. Cos 3x over 3. Minus integral, this time I'll put v prime. My v is e to the 2x. So my v prime is v differentiated, that's 2e to the 2x. And I restate now my integral of u, which was this, minus cos 3x over 3. So I restate this. So I restate minus cos 3x over 3. But the double negative, I turn this to positive. So this becomes cos 3x over 3 dx. And let me just repeat the process again. So, repeating again. The integral of e to the 2x sine 3x dx is equal to, so this would be minus e to the 2x cos 3x over 3 plus, and again I'm going to apply by parts to this again. So again, this I'm going to let this be my u again, and cos 3x over 3 will be my v. So my u, I restate it, I end up with 2 e to the 2x and then my cos 3x over 3 now, I'm going to integrate that. I end up with negative sine 3x over divided by 3 again. I end up with 9 now in the denominator. This negative, then put this negative here. So this negative and positive give me negative. So let me just put this negative out here. Minus the integral. This time I'm going to put my u prime now, which is 2e to the 2x differentiated. That's 4e to the 2x. And of course, I restate my integral of u, which was this sine 3x over 9. Well, negative sine 3x over 9. So of course, negative sine 3x over 9. Double negative again, positive. So it's actually sine 3x over 9 dx, of course. So we can do some grouping now. You'll recognize that this is integral of e to the 2x sine 3x. Also integral of e to the 2x sine 3x. We can group both of them on the same side. So we end up with, an error was made here with the sign. Integrating cos is actually positive sign. So this should be positive. It should be positive. And this would have to be negative. Alright, since the integral of cos is actually positive sign. Alright, so let's move. So let's group. So we end up with integral e to the 2x sine 3x dx. Group is on the other side, becomes plus. I'm going to put the constant outside, 4 nines. So plus 4 nines integral e to the 2x sine 3x dx. And then we have our terms here, minus e to the 2x cos 3x over 3. And here, plus 2e to the 2x sine 3x over 9. Continuing, so we will group these terms. So this is, let's look at this as, at these two terms, this as 9 over 9. So when we add these two like terms, we actually get 13 over 9 times the integral of e to the 2x sine 3x dx equal to the right hand side there. Just restate these. So just restating these. And of course now to get rid of the 13 over 9, we can times both sides by the reciprocal, which is 9 over 13. So I'm going to times both sides by 9 over 13. So we end up with e to the 2x sine 3x dx equal, multiply this side also by 9 over 13. So 9 over 13 times both sides times 9 over 13. So 9 over 13 times the first term, well, 3 into 9 is 3, so that it will become negative 3 over 13 e to the 2x cos 3x, and multiply this by 9 over 13, 9 cancel 9, so we're left with 2 over 13 e to the 2x sine 3x. So that's about it. Next, use the Marvel's theorem to show that 1 plus 3i to the power of 4 is equal to 28 minus 96i. So we first need to rewrite. So we're going to let z equal 1 plus 3i, and we're going to rewrite in what we call the polar form. So we need r. So r is square root of 1 square plus 3 square. So that's root 1 plus 9, that's root 10. And we also need theta. Theta is tan inverse the y over the x, so tan inverse 3. And in radians, tan inverse 3 is 1.249 radians. So it means therefore that 1 plus 3i is equal to, and the let me just write out the polar form in terms of the form. So polar form, z equal r cos theta plus I sin theta. That's a polar form for the complex number. So z, we have 1 plus 3i. R is root 10 cos theta, 1.249 radians. So we're asked to find 1 plus 3i to the power of 4. So I'm going to raise both sides now to the power of 4. Let's raise both sides now to the power of 4. So the Marvel's theorem says that 1 plus 3i to the power of 4. The theorem says that we raise r to the power of n. So we raise root 10 to the power here of n. N is 4. And then cos. And we're going to multiply now 4 times, multiply the angles by 4. So r to the n. So 4 times the angle. So 4 times 1.249, that's 5. So root 10 is root 10 to the power of 4, that's 100. So we have 100 outside the bracket, so 100 cos 5 plus 100 I sin 5. And where the 5 came from? 4 times the angle there. Remember the Marvel's theorem? R to the n, cos n theta, sin n theta, where n is 4. Alright, so expand, we have 100 cos 5. Well, we have 100 cos 5 already, so we just need to work that out in our calculator. Remember, 5 is in radians, so 100 cos 5, that's 28. So 100 cos 5, that's 28. And 100 sin 5, that's negative 96. So 28 minus 96i. So the proof is complete. Part C, derive the reduction formula. Integral of sine x to the power of n is equal to all of that here. So again, this seems to be a little bit of by parts mixed. So we know the integral of sine x to the power of n is dx. We know this is equal to, let me just write it to the right. We know this is equal to, we can rewrite this as the integral of sine x times sine x to the power of n minus 1 dx. So we rewrite that losing the laws of indices. And then now we're going to do integration by parts. So again, using my integration by parts formula. Alright, let me write my integration by parts formula again. So the formula I'm using says the integral of u times v is equal to, or v times u. Let me put v times u. Well, it doesn't matter the order. So v times u. So I'm going to integrate, I'm going to keep the v and integrate u in the first piece minus integral, I'm going to differentiate v, and this integral I have here for u, I'll repeat it here. So this, I'll call this my u, sin x my u, the other term there my v. So integrate u, integrate sine, that's minus cos, and I keep my sin x to the power n minus 1. Minus integral, and this time now, I'll differentiate, well, I'm going to repeat now the integral of u, which is the negative sine x to the power n minus 1. So a double negative, with a plus sine x to the power n minus 1. And my v prime, my v was sine n minus 1. Sin x to the power n minus 1, I'm going to differentiate that using the chain rule. So I end up with n minus 1. I'll put the n minus 1 outside here. I end up with n minus 1, put it outside here, times sine x, and I subtract 1 from my power, n minus 2, differentiate sine, you end up with cos. So that's chain rule applied there. N minus 2. So sine n minus 2. So remember, I subtract 1 from the power. So again, n minus 1 times sine, subtract 1 from the power. So it's n minus 2, differentiate sine. So we're differentiating this. Sine x to the power n minus 1 using the chain rule. So n minus 1, sine x to the power of n minus 2, differentiate sine, we get cos. So we end up with that thing there. And I made that area, by the way. The integral of u was negative cos. So, it's negative cos actually. So this should be cos x. Since the integral of u, negative cos, the double negative went up with plus sign. So that should be what we have there. Let's continue. So what we have here is minus cos x sine x to the power n minus 1 plus, and we have n minus 1 out here, times integral cos square. So this is cos square. So cos times cos is cos square. So what we can do is rewrite the cos square as 1 minus sine square. So what we have here, so let me put this first. Sine x to the power n minus 2. So sine x to the power n minus 2 times cos square. But cos square, we can rewrite cos square as 1 minus sine square. So rewrite the cos square x as 1 minus sine square x as the first of the Pythagorean identity. dx. So we end up with minus cos x sine x to the power n minus 1, sine x to the power n minus 1, plus n minus 1. And what we can do now is expand this, expand the bracket. So this becomes sine to the power n minus 1 times 1. So we distribute that. Sine x to the power n minus 1, we get sine x to the power n minus 1 times 1. We get back that. And then sine x to the power n minus 1 times, well, this is n minus 2, not n minus 1. That's n minus 2. Keep making error with this thing here. It's n minus 2 times 1, so n minus 2. And then sine x to the power n minus 2 times the other term, that's sine x to the power n. Because law indices add the powers, negative 2 cancel 2, so you just know sine x to the power n dx. Good? Alright? So next, we can separate the terms. So we have cos x sine x to the power n minus 1 plus, so we can, so the integral, we can separate them. So this is n minus 1 times the integral of sine n minus 2 dx minus, again, separate n minus 1 times the integral of sine x to the power n dx. So we break it up, alright? And then now, remember on the right hand side, on the right hand side we have integral of sine x to the power n. Let's restate that. So on the right hand side, what we actually have is the integral of sine x to the power n dx. We can group this on the other side, on the left hand side. We end up with positive n minus 1 times the integral of sine x to the power n dx equal to, and what we have on the right hand side here, just restate this, that's cos x times sine x to the power n minus 1 plus, we have this n minus 1 times the integral of sine x to the power n minus 2 dx. So, we group these terms now, so we end up with on the left hand side, we end up with just n times the integral of sine x to the power of n dx. Since what we have here, so you have 1 of the term plus n minus 1 of the same term. And the 1 and the negative 1 cancel to just give you n. So it's n times the integral of sine x to the power n equal the right hand side plus n minus 1 times the integral of sine n minus 2 x dx. And of course now we can divide what we were asked to prove again. So now we can divide both sides by n. Divide both sides by n. By the way, the first term here was a negative term. This term was a negative term. So minus the cos x, this was a negative term. Negative term. Alright, so this was a negative term. The first term was a negative term. So divide both sides by n. So we're going to divide both sides by n. We end up with n cancel n. So we end up with the integral of sine x dx is equal to, well, just to write like the way they have it, 1 over n, that is negative 1, cos x times sine plus n minus 1 over n times the integral of sine x to the power of n minus 2 dx. So that's a proof. Okay, that's a proof there. Part of the question, hence or otherwise show that the integral of sine x to the power of 6 is equal to all of this thing there. No. So we know that the integral of sine x to the power n dx is equal to, let's restate it, where it is equal to negative 1 over n all of this. So let's rewrite that. So you write that down there. Alright, so this we were given from the onset. So the integral of sine to the power of 6, we're simply going to replace n with 6, so we're going to let n be equal to 6. So what we have now is the integral of sine x to the power of 6 dx. We simply substitute now 6 for the n, so negative 1 over n become negative 1 over 6. Sine 6 minus 1, so that's sine to the 5th power x times cos x, plus, if n is 6, 6 minus 1, that's 5, over n, that's 6. Integral of sine 6 minus 2, which is 4. Alright? So this is what we're actually to prove. So notice the proof of a sine square. So this sine to the power of 4, we need to rewrite also. So let's now find the integral, where the integral of sine to the 4th power equal to, so this time now, in the formula, we're going to replace now n with 4. So for this now, we're going to let n be 4. Alright, you applying this formula. So just find sine x to the 4th power integral. So negative a quarter. Sine to the power of 4 minus 1, that's 3. Cos x plus 4 minus 1 over 4, so that's 3 quarter. Sine 4 minus 1, that's 2. Sine square x dx. Alright, so what we can do now is simply substitute this. So we're going to substitute all of this now into the original sine to the power of 6. Right, so therefore, the integral of sine x to the 6th power is negative 1/6 sine x to the 5th power cos x plus 5/6 sine to the 4th power. Integral of sine to the 4th power, but we know the integral of sine to the 4th power is this, what we have here, circle up. So sine to the 4th power, let's rewrite it. That's negative a quarter sine cube x cos x plus 3 quarter times the integral of sine square x dx. Alright, so we end up here now with the integral of sine x to the 6th power is equal to negative 1/6 sine to the 5th power x cos x. Distribute the 5/6. Well, should be a negative term, a first term. Distribute the 5/6. So 5/6 times that, that's negative 5 over 24. 5/6 times a quarter. Sine cube cos x, and then we multiply by 5, 6 now times 3/4. 5, 6 times 3/4, that's 15 over 24. Divided by 3, that's 5 over 8. That's 5 over 8 times the integral of sine square x dx. Is that what we're asked to prove? Yes, that's the exact thing that we're asked to prove. Alright, so, yes, that's that.